No, don't guess now. Have a think about it.
When I make my first laptop, I'll give you one.
Ah, that's nice of you. And I know she said when and not if.
When?
Yeah.
Not if.
Yeah, so
I will do it.
so when you do,
Yeah.
I'll probably still be here. Just send one to the school, addressed to Stephen, no problem.
No problem.
Alright, do you have the first one finished now? No.
What?
Say what? Come on.
It's 1 minute.
Grace, do you have the first one finished?
No.
What's taking so long? What answer? Show me your answer.
I'm writing down the
Where's your calculation? Looks good. Looks good. Looks good. Yes. Okay. Do we have an answer yet?
Yes.
Oh my goodness.
Yes, I do.
You do. Kojo does. Kojo 1. Now you see, you're not too far away, but you're still, this number here, 1.2 is not right.
Yeah, no.
But you're not far away. Hmm? No. Grace, do you have an answer?
No.
Amanda? Nearly. Sohi? For question 1, huh? You have an answer. You almost have an answer. What answer do you have, Grace? Sorry, Amanda. Yes? No. No. Alright, I better do this. You make teacher worry. You make teacher worry. You make teacher worry.
Really?
Sometimes you make teacher worry.
Definitely.
All the time teacher worry. Alright, look up. So what happens here is she has a string and it's 30 centimeters long, and she plucks the string. That means she pulls the string and it begins to vibrate. So how big is the wavelength here?
B over.
Yeah, what's the answer for the wavelength?
I know, let's use
It should be 60 centimeters.
Why?
Well, this is only half a wavelength.
Oh.
The other half wants to be here, although it can't. I think this is the problem, was it, Amanda? So, that equals 0.6. You know that V equals lambda F. So that means F equals V over lambda. Does anybody remember how fast sound is? 340. Yeah. 340 divided by 0.6567. So the answer is 567 hertz.
Can I just make lambda? Lambda, how do you get it?
This, look closely, this here is only half a wave, because a wave should go up and then it should go back down again like this.
Why is it 560?
Is it not?
Yes, it's 567 or
I just typed it in.
566.7.
567, 566.66.
Yeah, 66667.
Just show me. Show me what?
Did you write down the?
Yes, of course I did. 3 significant figures as normal.
Is it in degree mode?
Yeah, it doesn't matter about that. Right, okay, so that's concerns your teacher. Why don't you try the second one now?
Number 2.
So I shall pause this. Okay, so in number 2, you have your pipe like this, And
Did you play?
no, I didn't. Don't need to. And there's antinodes at the end, and 2 nodes in the middle. Anyways, it doesn't matter. You have exactly 1 wavelength in the pipe, don't you?
Mm-hmm.
From here to here. So you know that lambda equals 0. What number?
3.
Is it 30?
Yes.
Okay. In the new version, I changed it to 40. Not that it matters. So since I changed it to 40, I'll do it as 40. But your answer is right, okay? I'm just changing it to 40.
So lambda equal x.
Question, Sohi? Yeah.
Why is this?
Yeah, the reason is in the question I said it was open. So, you know what I mean by open? Like the air can go in, there's a hole. When it's open, there's always an antinode at the end. So here is an antinode, and here is an antinode. So this is the smallest wave I can draw that has an antinode at the start and at the end. For example, I couldn't do this. Oh no, I'm not even going to try. Yes, I don't know what else to say. These are antinodes at the end because they're open. If it was closed at one end, then it looks like this. You have a node, and then and then you have an antinode. But it's because it's open at both ends. You don't seem happy. You're not happy. Tell me what's confusing you.
So, if they're both open,
Yep.
it's always like that.
If they're both open, there's always antinodes. So if one is open, then you put an antinode there, and if it's closed, you put a node. So for example, if it was closed at both ends, you would have a node and a node, and the antinodes would be in the middle.
So what is the wavelength?
The wavelength,
If you draw the picture like this.
oh, the one I just drew,
Yeah.
that's one wavelength.
One.
Yeah.
The wavelength is just you look the notes, 2 notes.
I guess the way I do it in my head is I see if I have one wave. So for example here, I have top, all the way down, and then back to the top. So that's one wave. Yeah, top to top is one wave. Yeah. Whereas here, it's middle to top. That's only a quarter of a wave, because then it still has to go top to middle, and then middle to bottom, and then bottom to middle. I know I know it can be tricky. Yeah. Yes. Shall I continue? In my version here, I said the wavelength is 40. Although I know in the one I gave you earlier today it said 30. Yeah?
Yes.
It doesn't matter. It doesn't matter. I'll just do 40 now, but your answer is right. No, you don't need to change anything. Yours is right, okay? So you have V equals lambda F, so F equals V over lambda. So I get F is 340 over 0.4, which is 850. Now, wait, if you change that 0.4 to 0.3, you do get 1133, okay? The reason I changed it is because I didn't want the same number as question 1, which was also 30 centimeters. That's why I changed it at lunchtime. Yeah?
Question
Number 3, yeah? No, number 3 now. Yeah. Let's have a look.
Yes, please.
So what you have here, well, firstly, the frequency is what? The frequency is 1,100.
Yeah.
And because it's sound, you know that the speed is 340. And you know that V equals lambda F. So therefore the lambda is V divided by F.
3.24.
What did you get? 0. 309, yeah. What do you mean, wah? I just divided numbers. Did you not get this for the first part?
Oh, I make it so difficult.
No, I'm not finished yet. I'm not finished.
I make it so difficult.
So, let's draw this. Which harmonic is this?
3.
The third harmonic.
Yeah.
Third.
So, here do I have node or anti-node? Node. And here I want to finish with an...
Anti-node.
Oh my goodness, okay, let's try.
Make that easier.
Yeah. Okay, hang on, let me count as I go along. So, this one is the first harmonic. Then this one is the second, the third, the fourth, and the fifth.
What?
Yes.
4.
No, let me explain. Let me give you a little, hey, I'm going to give you a trick, okay? What is the first harmonic for this? It looks like this, doesn't it?
Yeah.
We did this one in class. So the second harmonic is 2 of these. The third harmonic is 3, and so on. So if I go back here, this is the first harmonic, okay? This is the second harmonic, which is not possible because it finishes on a node. This is the third harmonic, which is possible. This is the fourth harmonic, which is impossible. And then this is the fifth harmonic, which is possible. So how many wavelengths do I have here?
5.
I have 5 quarters. 5 quarters of a wavelength is equal to 0.309. So the wavelength, no, sorry, I don't mean to say wavelength. I do mean to say wavelength, not 309. I wrote that wrong. 5 quarters of 0.309 is equal to the length of the pipe, because 5 quarters of a wavelength is what I have. My goodness, let me write properly. This is 5 quarters a wavelength. So that equals so I have 0.386. Wait, no, nobody corrected me. What? What do you mean what? This says it says it's the third harmonic.
Yeah, I was telling you.
No, you weren't telling me this.
I did.
So I said why?
Yeah, but you. But I don't understand what you mean when you say why. You need to say, but teacher, why this if it's the third harmonic? I'm not that talented. All right, let's try this again. Right, let's draw 3 third harmonics.
But they're also 5.
I know, that'll be the next part. 1, 2, 3. And it's like this. Alright, that's better. So how big is this? It's 3 quarters a wavelength. So that means this will be 3 quarters 0.309, which equals so the pipe is 0.232 meters long. Ow. So the question is, what is the frequency of the fifth harmonic? Okay, so the fifth harmonic would be what I had a moment ago. So, can I go down a bit? Well, I'll wait. Okay, can I go down? Yes, Amanda? Well, maybe I'll just squeeze this up a bit.
Okay.
Can I put it here like this?
Yes.
Yeah. Okay, so now we want to draw fifth harmonics. Okay. Okay. 1, 2, 3, 4, 5. Now, how long is this? Well, this is still 0.232, isn't it? Yeah. So we have now 5 quarters a wavelength equals 0.232. So the wavelength equals 4 over 5. So here we get the wavelength is equal to 0.185 meters. And V equals lambda F. So that means F equals V over lambda, which equals 340 over 0.185. And you get the correct answer, which is 1833 hertz.
1837.
No, I'll stick with that. It makes me happy. 1833 roughly. Well, look, if you're doing the 3 significant figures anyway, so it would just be 1830.
No, 7 would be 40.
It'll be 1830.
40.
30. Okay. Right, try number 4, please. I'll do it. Yes? So, what's happening here is she has a machine and it's making some sound here, and the machine is operating at 240 kilohertz, but that's actually per minute. So I actually should really just say 240 kilo rotations per minute. Anyways, we must divide it by 60 to make it per second. So I shouldn't really have hertz there. So that would be 240 divided by 60 is 4 kilohertz. So the first thing was just to make it per second instead of per minute. Now, what's happening here? Do you know what they mean by ear canal?
Close at one end.
Closed at one and open at the other, yes. Look up. Look. This here is your ear canal. Let me draw it here. Yeah, here's your head, okay, and then here's your ear, and then here's the rest of you.
Looks nice.
Steven.
Yeah, that's me. And then your ear canal is a small little pipe for hearing, and then at the end is a little drum. So what happens is the sound comes in, but it sounds really loud. And the reason it sounds really loud is because if you look really closely, what's happening is this. This is open here, and this is closed here. And there's a standing wave made like this. It's hard to draw, sorry. Which is 1/4 a wavelength. Sounds like this in your ear sound really loud.
Yeah.
When you have a first harmonic in your ear, it sounds really loud. Even though it might not be very loud, it sounds really loud and painful. It's harmful because your ear starts to vibrate.
Yeah.
Just like my example with the pipe, it vibrates when you strike it with the right frequency. So anyways, we know the frequency, so we can know the wavelength. And we know the wavelength, so we can know how big her ear is. So we have V equals lambda F. 340 equals lambda times 4,000. So lambda is equal to 0.085. So that means a quarter lambda, which is her ear size, is equal to 0.02125, which is roughly equal to 2.1 centimeters. 2.1. Does anybody have internet on their phone? Yeah, I want you to type in this 4,000 on YouTube. Somebody find this for me. 4,000 hertz test sound wave. Or you might even have to type in, well, just try 4,000 hertz test sound wave. And, yes. Now, don't all play at once, so tell me when you find it before you play it.
Found it.
Battery's gonna die.
This one. Shh. Now, is the volume up? You got 1%. Alright, let's do this. Listen.
No, that's
Higher, all the way.
Nice.
And you can stop.
I just saw.
Huh? Now, you play it on yours. Doesn't sound nice, does it? Volume all the way. Maximum. Oh, yeah. Don't like that, huh? And stop. So this sound wave is this sound wave is 4,000 hertz, and at this frequency your ear starts to vibrate because a standing wave, a stationary wave, is formed inside. So your ear actually starts to vibrate at this. So it doesn't have to be very loud, because your phone is not very loud, but it can still sound very painful and loud. Yeah? Not good, huh? I know what you're thinking. Don't play it, okay? All right, I'm going to do number 5 because I know you'll have trouble doing it, okay?
No numbers.
Oh no, there might be time. Number 5 is very short.
When is the 1, 2, 2?
I don't have my text yet. So what's happening here is you have a radio tower, radio, and there's another radio tower here. And yeah, and there's a radio wave coming out of the first tower, and in fact there's a radio wave coming out of the second tower. And what happens is a standing wave is formed. Now, at the beginning, do we have node or antinode here? It'll be node, and then here is a node, and here is a node. And in between, antinode, antinode, and here is antinode, and then here is node, etc. Now, if this was to happen, if you had... Now this, listen, this is not realistic because you don't usually have 2 radio towers like this. But if you did have 2 radio towers with the same radio wave, they could make a standing wave like this. And this is quite bad for the car because if you were driving along here, your signal would go from being weak to strong, weak and strong, because every time you pass a node, there's no signal. and there's only a signal here at the antinodes. So if you were like listening to the radio, it would go from being louder to quieter, louder to quieter.
Fringes.
Not fringes because it's not diffracting,
Yeah.
but it's a similar idea to fringes of periods of loud and quiet. Now, in the question, I tell you that the distance between each node is 43 seconds, and your car is moving at 120 kilometers per hour. So here's the car, and after 43 seconds, how far has it traveled? If it's going 120 kilometers an hour, and it's 43 seconds. So we need to convert this into meters per second. 120 times 1000 divided by 3. That is 33.3 meters per second. Probably should, huh? So he travels for 43 seconds. So the distance here is 1433 meters. So that means the distance between the antinodes and nodes is 1433 meters. Now, do you remember in my picture of the standing wave, what's the wavelength if you know the distance between the nodes or the antinodes? Let me tell you now, this 122 business. 122, I don't think you'll get it. It's at 453.
Oh, Steven.
I'm so sorry. I'm so sorry. Anyways, you walk very slow. You would never get there in time. KJ, be supportive. Right. Yeah.
What did you say?
What's what?
We should
Kilometers per hour. Sorry, that's very messy. Now, do you remember if you know the distance between the nodes or the antinodes? If you know the distance between the antinodes, or if you know the distance between the nodes, you can calculate the wavelength. Do you remember what it is? Yeah, so in other words, lambda is just twice this number. So the lambda is 2867 meters. Now, we have to use this formula, V equals lambda F. So F equals V over lambda. Now, what's the V here?
340.
No, because this is a radio wave. So the V is 3 times 10 to the 8.
Is it there? How are we supposed to know?
Because I said it's a radio wave.
So we're supposed to know the figure.
It's speed of light.
Oh.
Oh yeah, forgot about that thing we did last week. So this here is equal to 104,651 hertz. Or if you want, it's 104.6 megahertz.
Can we hear that?
No, you can't hear it. Your radio can hear it and convert it into sound for you, but you can't hear it.
6, please.
Now, I'll do 6, and then we finish.
Yes.
Now,
7 minutes.
I'll do it in 3. So, can I continue?
Yes.
No. Do you have this? Do you need to write something here, Grace? I'll give you the time it takes to drink my coffee.
You watched the video.
That's if I upload it.
What?
Maybe I want to run straight home and not go back to the office.
No, you don't.
Yeah, you're right. Okay, can I go on to 6 now? Hang on, I still have a little more coffee, but it's running out.
Okay.
It's looking empty. Okay. Now, do you remember here how much of a wavelength is this? It's a quarter, isn't it? You don't need to, well, you can draw this if you want, but just to refresh your memory, this is a quarter of a wavelength, yeah? So let's say the length of the pipe is L, then the wavelength would equal 4L. Isn't that right?
Exactly.
Yep.
Y for F? Ah, okay.
Yeah, it makes sense, doesn't it?
Yeah, it makes sense.
Now, if you do this experiment, you'll actually discover that it's accurate, but it's not 100% accurate. There's a small error. It's actually a little bit different. Now, it's very small, but you can actually measure it. Okay, so what we're going to look at is calculating that error. Okay, can I go down? So, firstly, you have 3 harmonics. 1, 2, 3, and then secondly you have 5 harmonics. 1, 2, 3, 4, 5. Here the frequency is 1100, and here the frequency is 1800. Here the V is 340, and here the V is 340. Here the lambda, V equals lambda F. So lambda is V over F, and here lambda is V over F. So what's the first one then? V 0.309, and here the lambda is 0.1889. Yes? Now remember I said there is a small error though. So in fact, it's not quite this, and it's not quite this. There's a small error though. So if you want, you can say it's roughly equal to this, and it's roughly equal to this. In fact, what you have is, you actually have it like this. Lambda is roughly equal to 0.309. Hang on, I'm getting confused. Oh yeah, sorry, I shouldn't call these, I should give them different numbers, lambda 1 and lambda 2, so I'm not very confused. Lambda 1 and lambda 2. Okay, so lambda 1 is roughly this, plus the error, which I'll call E, and lambda 2 is equal to 0.1889 plus the error. Say again? Yeah, if you do this experiment in real life, what will happen is, if I go back up here, if you look up, Grace, a little bit of the wave is actually outside of the pipe. So it doesn't, there's a little bit, very small bit, that's outside the pipe. And the reason for this, it's very complicated, and it's enough to say that it's because of the edge here. The wave doesn't fully fit inside. It's nearly a quarter, but if you do this really in real life, a little bit of the wave will be sticking out. Okay? So it's a small error. It's very, very small, but it's still there. Okay, now, if you look back here, this pipe has length L, and this is the same pipe, so it has the same length, true?
Yeah.
So here, the length of the pipe would be how many wavelengths? It would be 3/4 a wavelength. And here, the length of the pipe, how big is it? How big? 5/4 a wavelength. So you have 3/4 0.309 plus E, and here the length is equal to 5/4 0.1189 plus E. Now what do you think you do next here? This is an E. Yeah, because they're both equal to L. So now you have 3/4 0.309 plus E is equal to 5/4 0.1889 plus E. Is this enough information to get the E?
Yes.
It is. So you can solve this. 3 times 0.309 0.927 plus 3e equals 0.9445 plus 5e.
After we,
Yeah, you can just solve this easily.
yeah.
So the e is equal to minus 8.75 millimeters. So there's a very small error.
Minus.
Yeah, minus meaning that the wavelength is a little bit smaller than what you thought. You should reduce it.
I see.
So, yeah. Yeah.
Happy.
Happy? Happy.